All right, let's look at one more example of finding the Taylor series for a function that we've seen before. And so we'll look at the Taylor series for cosine of x centered at x equals 0. And then we'll try and use that to figure out the Taylor polynomial of degree 5. And so I'll start this by doing another table where I can hopefully find the pattern of the derivatives for my function. And so I'll want to write out the first few derivatives. And in general, you're just going to write enough derivatives until you can see whatever the pattern is between the derivatives. And so that might depend on the function. You might need more derivatives for some more complicated functions and fewer derivatives for simpler functions. And in this case, it turns out that 4 will be enough, but you might not know that to begin with. You might just have to keep on writing them until you can see. And so here, if f of x is cosine of x, and then if I take a derivative, I'm going to get minus sine, and then another derivative will give me minus cosine, and then another gives me sine, and then another one gives me cosine. And so I know I can stop here because the function has sort of cycled back around. And so if I kept on writing more values in the table, they just repeat the same pattern at this point. And so now I want to plug in wherever I'm centering, which in this case is x equals 0, into all of these derivatives, because that'll be helpful to find the Taylor series in a minute. And so when I plug in x equals 0, I get 1, 0, minus 1, 0, 1. And if I wanted to, I could keep on writing out this pattern because I know that it's just going to keep on cycling. All right, so now I need to use this table of derivatives and plug it into the Taylor series formula in order to figure out the final Taylor series for cosine. And so the nth term in my Taylor series should be the nth derivative evaluated at 0, because I'm centering at 0, over n factorial times x to the n. And now I'm just going to use my table in order to figure out what these various terms should be for different values of n. And so, in other words, I'm going to plug in n equals 0 into this formula and simplify it. And so if I plug in n equals 0, then I get whatever the 0th derivative is, evaluated at 0, over 0 factorial times x to the 0. And so here the 0th derivative is just the first value in my table, and so that's a 1. And then I'll do the same thing for n equals 1. And so I'm just going to read off this value from my table. That should be a 0. And then I'll do the same thing for the next term. And so that's a minus 1 over 2 factorial x squared, plus a 0 over 3 factorial x to the third. And then maybe I'll write down one more here. And so that would be a 1 over 4 factorial x to the fourth, and then plus so on indefinitely. And so now that I've written out the first few terms, I can see that a lot of them end up just being 0. And so it'll be helpful for me to simplify this by writing out only the terms that survive. And so the first term is just going to be a 1. This x to the 1 term ends up canceling. And so the next term, and I should have written a minus sign, is going to be a minus x squared over 2 factorial. And then the x cubed term goes away. And so the next term will be x to the fourth over 4 factorial. And at this point, hopefully you can see the pattern. But if you can't, that's okay. Just write out a few more terms in the previous line. But it's going to keep on alternating signs. And the power is going to move up by 2 every time. And so really this is a representation of the Taylor series as written, but I would like to rewrite this in summation notation so that I can have it written more compactly. So in other words, I want to write it somehow as the sum from n equals 0 to infinity. And so in order to do this, I need to analyze what's happening between each term. And so the first thing is that I can see that the powers on x are increasing by 2 every time. And so that means that I'm probably going to have something that's close to x to the 2n in my series. And now I just need to check that this works for the first term. And so when I plug in n equals 0 into x to the 2n, I get x to the 0, which is 1. And so that does agree with the first term here. And then every time n increases by 1, I'm just going to increase this power by 2. The next thing I can observe is that it's always the case that the factorial and the power are the same. And so that just means that I'm going to have to divide by 2n quantity factorial. And so I'm almost done, but the only other thing is that this does alternate signs between every term. Or in other words, it's just plus and minus, plus and minus. And so that means that I'm definitely going to need to have a minus 1 to the n or something close to that in order to have the correct signs in every term. And so the choices are really, it could be a minus 1 to the n or a minus 1 to the n plus 1. And the way to determine which one it is to just plug in n equals 0 and make sure that it works. And if it doesn't, then I'll just switch it to the other one. So if I plug in n equals 0, minus 1 to the 0 is a positive 1, which does match with the sign of the first term, and so I'm good to go. And so this expression right here is the Taylor series for cosine. At this point, if I want to do the rest of the question, which is figure out that fifth order Taylor polynomial, then all I have to do is write out all of the terms in the Taylor polynomial that have degree 5 or less. And so in this case, that's just 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. It is the case that there's no x to the fifth term here. That's fine. It's still the fifth order polynomial because that term is just 0. So it's sort of secretly there, but the coefficient is 0 anyway. And so this would be the fifth order polynomial. One more thing I should mention is that in the problems we just did, I found the Taylor series before finding the Taylor polynomial, just because the Taylor series was easy to find to begin with. In some examples, it'll be so hard to find the Taylor series that maybe you're satisfied with just finding the Taylor polynomial on its own. And so it is the case that I could have used this table of derivatives right here to figure out the fifth order Taylor polynomial by just cutting it off after I had found 5 derivatives. And so it really would have been right where this red line is. And then just plugging into the formula to figure out the first 5 terms. And so sometimes you'll have to do that just with the table because maybe the table doesn't have a clear pattern, but you can still figure out the Taylor polynomial by using the table anyway.